Thanks so much for the introduction, and thank you for inviting me to join. It's always fun to talk with other people in mechanics. So I'll talk to you a little bit about some part of my PhD work at Caltech, working with Professor Nadia Lapusta and Daniel Faulkner at the University of Liverpool Rock Deformation Lab, looking at applying our computational models to understand critical stress conditions for frictional ruptures and earthquakes. So a lot of my work really focused on fundamental questions of what factors control how an earthquake rupture starts and how large they may become, right? So essentially trying to understand the source component that goes into hazard models for the strong ground motions and surface deformation that you get from an earthquake, as well as other types of hazards like landslides. And so one of the major focuses that I do is I look at particularly conditions for large earthquakes, because large earthquakes are very rare but have great potential for widespread damage. And as we've seen over recent decades, we continuously have these large earthquakes that challenge our understanding of where and how large earthquakes can occur, such as the 2011 Tohoku-Oki earthquake that had a bunch of slip displacement in the shallowest extension of the subduction zone here, and that was previously thought to be stable and couldn't host earthquakes, and that was ultimately what resulted in the very large tsunami. And also these kind of questions are focused for qualitative differences in hazard assessment, such as when we look at California and the San Andreas Fault, we ask questions of, will a large earthquake be more likely to impact Los Angeles on its own, or San Francisco on its own, or could it potentially rupture the entire span of the fault and hit both? And that leads to qualitatively different changes, different assessments for hazards and preparation, right? Not to mention most of our infrastructure, like our water systems, cross the San Andreas Fault in multiple locations. So when we look at developing physical models of faulting and earthquakes, we can kind of come back to this very simple classical conceptual model of the evolution of motion, shear stress on a fault, where we think of this nice little toy model of a continuum bulk with it separated by a fault. So we have a nice little planar fault surface here that is undergoing some remote shear loading. And at different points along the fault, they'll be stuck over certain periods of time and build up elastic strain. And then eventually, it will lead to a rupture once you reach a failure criterion, and that will spread out along the surface. And so we often assume that faults are frictional interfaces governed by a Coulomb frictional relationship as shown here, where we have an effective normal stress being the difference between some applied normal load and a pore pressure, modulated through a friction coefficient. And we can often even simplify this even further to the single degree of freedom representation here of a spring block slider, where you imagine you have a block that is loaded along the surface and it's being pulled through a spring at a constant loading rate. Over time, you build up some elastic strain within the spring, and then once you reach the failure criterion, you have stick-slip behavior, as shown down here. And so these are very simple representations of frictional sliding and frictional rupture, but they're actually widely used in many studies to interpret seismological observations, because in these kind of simple models, you have this idea that over time you build up stress to some fixed static strength. Once the fault reaches the static strength, it will start to slide, it will fail, and drop down to a dynamic resistance level. And in both these kind of models, you imagine that the static strength and the dynamic resistance are proportional to some static and dynamic friction coefficient, the difference between these two being a well-defined property called stress drop. And ultimately what this model tells us is that if we were able to measure or constrain certain aspects of the system, like the stress drop or static strength, we might have some predictability about where we are in terms of when an earthquake will occur or any type of frictional failure process will occur. By the way, please feel free to stop me with any questions in the talk. So this leads to a wide variety of studies across all types of scales trying to understand the evolution of stress on faults, both in the lab and field. So this ranges from small-scale laboratory friction experiments, as shown here on the left. These are performed under a wide variety of conditions, looking at low velocity, low sliding rates down to nanometers per second, to relatively high sliding rates on these rotary shear apparatus up to meters per second. But these friction experiments, that's where we get most of our understanding of rock failure and friction. These are typically performed on very small samples of millimeters or centimeters, right? On the other spectrum, we have, end of the spectrum, we have these field scale inferences. such as seismological inversions from earthquakes of like the stress orientations along a fault, as well as heat flow measurements around faults. So that's what's shown here on the bottom, where people can try to back out friction coefficients due to shear heating. But these field scale inferences represent average quantities over large scales of kilometers, often hundreds of kilometers, right? And so they're averaged over space and time at a very different scale. And then only very recently do we start to have these intermediate scale experiments of tens of centimeters to meters where we can actually start to infer aspects of the finite rupture process here, such as super shear rupture or stick slip in these large meter scale block experiments. But ultimately, lab experiments are restricted in terms of the range of conditions that they can explore. So my work tries to develop computational models to also bridge different observations across these variety of scales from the lab to these large scale field inferences, and try to understand the relationship between average and local behavior from these inferences. So jumping into kind of the basic understanding that we have, from the lab, we perform all these different types of friction experiments, and what ultimately has been determined in the state-of-the-art understanding of fault shear resistance is that friction is actually quite more complicated than a simple static and dynamic friction coefficient, right? So if you do these velocity step experiments where you take an interface, you slide it at a certain sliding rate, and then immediately jump it to a higher loading rate, what you see is this initial increase or direct increase in shear resistance, and an evolution to a new steady state shear resistance level, this rate dependent friction effect, as well as the state evolution and this transient evolution to a new steady state with an increase in sliding. We also see that if we hold an interface for extended periods of time with negligible motion and then try to slide it again, that friction increases with time. And so these different features are encapsulated in these so-called rate and state friction laws, which incorporate both a direct dependence on the sliding rate as well as some evolutionary transient depending on the quality of contacts along the interface. And these laws have been actually very successful at describing behaviors of bare surfaces as well as granular layers. But one of the key points I want to bring out here is that in this framework, this notion of a static friction and critical failure condition is not really well defined because interfaces under shear loading are always sliding or creeping at some non-zero slip rate. And there are two qualitative features here that are important to highlight within this framework. One is that depending on how this friction level evolves, if in the case, I guess, shown here in this particular experiment, if when you increase the sliding rate, you drop down to a lower shear resistance level, this is called velocity weakening behavior, where essentially as you increase velocity, you decrease the shear resistance, leading to this positive feedback that promotes unstable sliding and potentially large dynamic events like earthquakes. In contrast, another type of behavior is what we call velocity strengthening, where when you increase the sliding rate, you actually increase the shear resistance. So this would be a negative feedback and promote stable sliding, potentially acting as a barrier to earthquake rupture propagation. So these are two qualitative different features that you can see for different interfaces depending on their material properties, as well as the temperature conditions, fluid content and such. But they're really useful trying to describe the stability of frictional interfaces and potential seismogenic behavior. One of the important features when talking about these friction laws is that they really only describe changes in the shear resistance, though, and often most of our observations seismologically relate to stress changes. And often a feature that's kind of left out of most modeling or understanding of these friction inferences is the dependence on absolute stress levels, and particularly related to temperature and shear heating. So if we take these rate and state friction laws and we were to simulate, just simulate some kind of like fault model, you get these frictional ruptures, and ultimately you only get a very mild change in shear resistance during these kinds of simulations. That's what's shown here in black. This is the average shear stress along a fault during a simulation. If we take typical friction coefficients around Byerlee values of friction of 0.6, and apply stress conditions that we expect at seismogenic depths at say 7 kilometers down along the fault, you get fairly high stress levels. And if we do simple calculations of shear heating and a temperature increase during reasonable earthquake scenarios, you'd expect substantial melt along the fault. Basically, if the shear resistance along that interface was anywhere higher than basically 5 or 10 megapascal, you'd expect that faults pervasively melt. And that's just not seen, particularly for the levels of shear that we basically are seeing. And this has led to, basically, there have been a variety of field observations that suggest that for mature large plate boundary faults like the San Andreas Fault, the average shear stresses have to be low, less than 20 megapascal. And this can't really be explained by typical rate and state measurements. These types of observations are related to the observations of extreme shear localization around faults, the lack of observed heat flow around these mature faults. This is often referred to as the heat paradox, as well as drilling directly down into a fault after a large earthquake. You see very mild heat signatures. So all these different observations suggest that we have to find some way of dropping the shear stress levels along the fault down to be very low, less than 20 megapascal. So kind of intuitive ways of doing this would be to either drop the friction coefficient. However, this is inconsistent with the types of materials that we see in the lab that actually produce unstable slip. So there are materials that have low friction coefficients, but they typically end up being this velocity strengthening, having this velocity strengthening response, and therefore would presumably inhibit earthquakes occurring. Alternatively, we could also drop the effective normal stress to be around 30 megapascal or lower, which would require significant fluid overpressurization in these faults, which is debatable if whether that's actually observed on natural faults. So this is a real question of how do we maintain these low stress faults? Luckily, the lab also gives us another type of observation, which is that this rate and state friction is not the whole story. That kind of realm, the rate and state friction typically is determined in the lab, revolves around these sliding rates less than millimeters per second. What this plot is showing here is the friction coefficient as a function of the sliding rate during these experiments. As we start to see this higher rate experiments, we see this dramatic shear-induced enhanced weakening at higher slip rates, up to around a meter per second, as would be related to earthquake sliding rates. So these go all the way down to a practically zero friction at high sliding rates. And there are many proposed mechanisms for this, many of them being thermally induced, such as flash heating of microcontacts or the thermal pressurization of pore fluids. But ultimately, this all argues that at high sliding rates, you can go down to very low dynamic resistance. And ultimately, this might be an explanation for low overall heat production during large slip events. So kind of to give an idea what this friction-induced shear heating and fluid effects would relate to fault weakness, we can imagine in terms of our effective stress here, if we wanted to make a fault persistently weak, we could just increase the pore fluid pressure along the fault. This is the fluids trapped within the granular layer in the fault. That could be persistently high, leading to persistently low effective confinement and shear resistance. Alternatively, we could dynamically weaken faults by basically having transient pressurization. So you can imagine that as you start to slip fast under high stress conditions, you start to produce heat. That's what's shown here on this right-hand term, this heat production term, that depends on the localization of shear and your stress levels, as well as how fast you're sliding. That would be modulated by thermal diffusion. And that can couple, depending on the compressibility of the pore fluids and the host rock matrix, into a pressurization of trapped pore fluids. So depending on the rock permeability and those relative compressibilities, you can have substantial thermal expansion of trapped pore fluids, which would effectively pressurize and unclamp the fault, leading to a dramatic reduction in the shear resistance during rapid slip. And so one of the important features of this enhanced weakening is that it leads to a substantial difference between this quasi-static and dynamic shear resistance levels compared to what we'd expect from standard rate and state friction laws. And in particular, for thermal pressurization, there's this prediction based off of simple theoretical considerations that with continued sliding, you'd have continued heat production, continued pressurization, and weakening with slip. So there really is no fixed dynamic resistance level, but it's really a product of the dynamics of the rupture process itself. So these types of, this observation is potentially useful because it could explain the discrepancy between typical Byerlee values of quasi-static friction observed at slow sliding rates in the lab, as well as these very low values of friction inferred from mature faults, saying around 0.1 or even lower. But a major question is how this relates back to average stresses inferred from earthquakes. So this plot is showing the static stress change inferred from earthquake ruptures. All these are individual earthquakes. And while there's a large spread here, one of the main observations that we have seismologically is that these static stress changes don't seem to have any systematic trend with the size of an earthquake or the amount of slip in an earthquake. And so one of the major questions is whether this type of continuous weakening would be consistent with these types of observations of basically magnitude-independent static stress changes. So essentially, this enhanced weakening is known to exist in the lab. The question is if it actually occurs on natural fault. So what my work tries to do is use our new computational models to incorporate these lab-derived rate and state-dependent friction laws, as well as enhanced dynamic weakening. We implement it into continuum models using a spectral boundary integral method, where we can treat full elastodynamic interactions through the bulk, wave media effects during frictional rupture. We also solve for the evolution of temperature and pore fluid pressure due to shear heating, and then we also have some approximations for off-fault plasticity during these ruptures. And what we look to do is simulate not just an individual dynamic rupture, but we use these rate and state friction laws to simulate long-term sequences of earthquakes and aseismic slip. So what this plot is showing is the cumulative slip along a fault over multiple sequences of earthquakes. So in red, these are contours of the evolution of slip during a rupture. So an earthquake is growing this way over time. Each of these contours here would be like 0.25 seconds. So very rapid slip. And then in black, you're seeing a seismic slip. So this are slow slip that can happen over months, years, tens of years. And so these simulations overall are basically simulating hundreds of thousands of years of slow slip as well as multiple earthquakes. And ultimately, we use these simulations to create catalogs of earthquake ruptures where we can study the evolution of shear stress and slip, as well as create catalogs of earthquake source properties to relate these seismological field scale inferences of stress to the actual properties that we see on the fault. That's our methodology. And now I'll step you through some of our simulation results. So one of the important things that we see in these simulations is that even in very simple fault models, we can get very complicated results. So a lot of the models I'm going to show today assume within this seismogenic region along the fault. So what I'm going to be plotting here is, once again, the spatial distribution of slip along the fault for 4 ruptures. And the right is the shear stress along the fault. Here in gray is before the rupture and blue is after the rupture. And so this is taking a little transect along the fault. And in these models, we're assuming that all the material properties are uniform, spatially uniform. There's no imposed material heterogeneity in these models. But what you'll see is that the stress distributions become highly heterogeneous when we have ruptures at different sizes, just due to the nonlinear relationships between shear stress and motion and the different sizes of events that we see. So we see for all 4 of these ruptures, on the shear stress distributions here, earthquakes nucleate in these very small regions of relatively high shear stress, and then can either propagate to become large earthquakes that span the entire fault, or stay as relatively small ruptures. So the gray area is showing the overall ruptured area, depending on what the stress distribution is ahead of the rupture, right? So if the stress conditions are favorable enough or high enough, the rupture will continue growing. If the stress conditions are low enough, the rupture will naturally arrest due to low stress conditions, and then leave this history of high stress for future ruptures along the fault. And this leads to ruptures of varying sizes that interact with each other through the history of motion along the fault. And so this already in a simple model, you can get a wide distribution of rupture sizes and very heterogeneous stress distributions. And one of the important details from these types of models that we see is that the conditions that are required to start an earthquake are very different from those required to propagate, right? So if we look at one single rupture here, just the evolution of slip through time, we can even look at the average slip being around 1 meter and the average stress drop being around 3 megapascal. And if we take different points throughout this rupture, we'll see that the evolution of shear stress with slip is very different, right? Where we have the rupture nucleating, it starts somewhere around this quasi-static resistance level, and then it will drop down, just kind of more or less monotonic weakening. Whereas points within the center of the rupture, where we have a kind of propagation of the rupture, are actually start at lower stress levels below quasi-static failure and are dynamically loaded and brought to failure and then will evolve. So they can even have more slip, but a smaller stress change, static stress change. And when we look at the edges of the ruptures where the rupture arrests, we'll actually have a negative stress change where the stress will be initially lower, and at the end of the rupture, it'll be higher than it was at the beginning. So all these effects are mediated by these large dynamic stress concentrations, as shown here in black, throughout the rupture itself. And ultimately what this is saying is that if we want to relate these average properties to this local behavior, we really need to understand how the earthquake rupture is starting, growing, and arresting ultimately. And these can all be very different. So one of the things that we find from these simulations is that if we take the average stress distributions before ruptures at different sizes in these fault models, the critical stress for rupture occurrence depends on the size of the rupture, as well as how efficient we have this thermal pressurization, this dynamic weakening within our models. So each of these markers is showing an individual earthquake, the average pre-stress normalized by this quasi-static stress, essentially the stress required for rupture nucleation. And so in blue and gray, these are models with very mild weakening, just standard rate and state friction. And as we go down here, these are simulations, fault models with more efficient thermal pressurization. And so essentially, as we have earthquakes of around the nucleation site, small earthquakes, they all have stress conditions more or less consistent with quasi-static failure. And as we have increasingly larger ruptures, these ruptures are occurring over large areas of lower pre-stress on average, and particularly as we have more efficient weakening, the stress conditions required for an earthquake to occur are much lower. So this shows us that these large fault areas can appear to be under stress with respect to conditions for quasi-static failure. However, they are still capable of hosting a large earthquake. And if we look at this in terms of a simple friction coefficient, this would give us this appearance of a low friction over these large areas, just due to this averaging over the entire rupture process. And one of the results that we see relating this back to the seismological inference of stress drop is that if we were to look at the spatial average of the static stress change before and after the earthquake, the ultimate result here for our simulations, this is looking at earthquakes of varying size as a function of average slip, is that the static stress changes are more or less magnitude invariant, as is seen for natural earthquakes. And so the result here is quite interesting. As expected for this enhanced weakening, as we have more efficient weakening and slip more during large events, you do indeed see this continuous weakening of the final shear stress after the rupture. However, because these ruptures are larger and are propagating over lower stress conditions, the average initial stress also decreases for larger ruptures, as we just saw in the previous plot. So these two features together end up leading to this nearly magnitude invariant static stress change, despite the fact that the absolute stress conditions are becoming very different in these ruptures themselves. And what this ultimately is telling us is that the seismological inferences of the static stress change doesn't really tell us much about the absolute stress conditions along the fault. It's not really diagnostic of that. So this brings us back to when we look at this conditions for low heat, low stress operation mature faults. We have these two end-member models, one where faults could be persistently weak due to fluid overpressurization, and essentially in this case, their fault is on average within one static stress drop from failure. Kind of very similar to that spring block slider model that we saw at the beginning. In the other case, we can have faults that are dynamically weak, where the stresses are very far away on average from static failure. So static failure would be up here around 60 megapascal. And the average stress, as plotted here in black on the fault, is very far away from it. You can have very low shear heating stresses, but as we just saw in the previous plot, you can still have comparable static stress changes during earthquakes. And that's because you have very small regions that nucleate up here, but most of the fault is actually down here and is dynamically driven to failure due to these very large dynamic stress changes. So I need to wrap up really quickly, but the last points I wanted to mention here is essentially studying individual earthquakes is very challenging, but there's potentially some insight to get from looking at populations of seismicity. So one of the things that we look at when we look at large fault areas is that we have a lot of small events, and typically they follow the scaling relationship called Gutenberg-Richter frequency magnetics, where it's a power law relationship. And this has been used to try to characterize, populations of earthquakes. Kind of to save on time, one of the features that we see from the scale dependence of the critical stress conditions of our fault models is that as we have more weakening in our fault models, larger ruptures are able to propagate over less favorable stress conditions. So essentially, one can imagine that for these fault models with more efficient weakening, it's easier for ruptures to become larger as soon as they start. And so one might expect that these faults will only have larger ruptures. And that's essentially what we see. Here I'm plotting the frequency magnitudes. So these are the distributions of earthquakes of different sizes in these simulations. And we see that for models with mild weakening, we get a lot of smaller events. As we increase the efficiency of weakening, we basically produce predominantly large earthquakes and fewer small events. So these population statistics are actually indicative or diagnostic of the efficiency of weakening along these faults, because the stress state is dropped away from nucleation conditions over most of the fault area. And this might actually be consistent with some mature fault segments, like the central section of the San Andreas Fault. So if we look at some specific fault segments that have hosted large earthquakes in the past, like the central section of the San Andreas Fault that hosted the 1857 earthquake, you basically see that while they had large earthquakes, they are absolutely no small earthquakes today and for our records. And so the paucity of small events on some of these mature faults may actually hint that they undergo this efficient dynamic weakening. And that's actually particularly useful because it could be a potential physical motivation for improving early warning systems, because these fault segments, if they are indeed governed by this efficient weakening, the probability of any given earthquake on these faults becoming much larger would be greater than based off of this typical power law Gutenberg Richter scaling. So I'm out of time, so I just want to wrap up here. And main point that I wanted to bring up here is that understanding the conditions for frictional failure is actually quite complicated, because the conditions governing rupture and nucleation can be very different from what's controlling how that rupture grows. And it actually depends on this self-organized scale-dependent stress conditions. But looking at population dynamics of these systems, we might be able to actually back out some of the conditions controlling how ruptures are growing or how efficient weakening can occur on these faults. So thank you very much for your attention. I'm happy to take any questions.